Okay guys, welcome to the first of these examples. Rather than spending time in lecture, we can take a little more time here, and then you guys have it as a reference to go refer back to. So today we're going to go over model formulation. We're going to use accounting as our example. How does money compound interest in a bank account? And we're going to go about it using kind of the methods we talked about in class. So first of all, we have our problem definition, where we're going to talk about, okay, what variables are we going to use, what are the assumptions we need, and then conservation laws. So what's must happen. So something like we can't just have money randomly appear in our bank account. We either have to add it in a deposit or withdraw it. Make sure it's a continuous model for our analysis. Then talk about our constitutive laws. So how are our variables related? So in this case, we'll talk about the relationship between time and that compounding interest and the value in our bank account. Finally, we'll talk initial conditions in this case. So the initial conditions are being what you have in the account to begin with. And then we'll look at the final equation and solution. So kind of the way we framed this problem is we're talking about somebody who's investing $1,200 a year in an account with 4% interest. So the first thing we're going to do is, number one, we'll define the problem. So we're going to define here A as our account balance, and A is some function of time. Right? We're not looking at the space money, we're looking at how the account balance changes over time. And some of the other variables that I'm going to refer to, W is our withdrawals, D will be our deposits, and finally I is any interest that we gain on the account. Okay, and one of the things that we know as well is we'll have some A at 0 equal to A naught. Okay, so this will be, and we'll talk about this one later as well, this will be our initial balance. Okay, we don't need to worry about control volumes here. I guess in a sense our control space is just that bank account. But we can go on to the next one here. So what are we conserving? So conservation. So the first thing with conservation, in this case, we know that in our account, so we need whatever the account at times t plus, okay, let's say we're going to look some step in the future. It needs to be whatever the account was at time t plus whatever interest we've gained, whatever deposits we've gained, and minus any withdrawals. Right, and we can, I'll set this up in a kind of a balance sheet as well. So at time t, and then our account value, some sort of interest, some sort of deposit, some withdrawal. Right, because we have, okay, so we have some money here, and then we have some other, we'll say point money here, let's say some other deposits as well. Right, and we want to add the interest, add the deposits, subtract whatever withdrawals we have. And then this will all equal our A at t plus delta t. So we'll get some $.dollar. Don't really care about the values. This is just for example here. But this is how you would keep track of things in your bank book. If you were looking to say, okay, what have I gained over this month? You'd look at, okay, I have interest of X amount, I have a certain amount of deposits I've put in, and I've spent all of this money. And then the next time you look at your bank account at the beginning of the next month, it would be whatever that final value would be, right? So we have this value now, and then you go through this process again. Okay, so this is typically how we view something like accounting. It is a rigorous method, so we're keeping track of every little detail here. the other thing is it's heavily dependent on t, or delta t. Now, unfortunately, this is something we have to deal with in the real world. We can't have continuously compounding interest on everything, but for this course, what we need to focus on is having a continuous function. So we need some sort of continuous function. Okay, and we'll go ahead and set that up. So here we go. Let's add a page. So step 3, we're going to make variables continuous. So in this case, we're going to take that equation we had before, so we know that our account at t plus delta t is equal to whatever our value was at t plus I plus d minus w. And then what we're going to do here is we're going to move that initial, or that account value at t over to this side. Okay, and we're going to say this is equal to I plus d minus w. Okay, now this is where we're going to take kind of a little bit of a logic leap. This isn't necessarily something we have to do each time we set up this these problems. This will be a step that is a little more natural when we get to things that are actually continuous. We're not talking about accounting. So bear with me here as we kind of pull some magic strings and we talk about, okay, well, with the change in my account with respect to time. Okay. But that is also times my delta t, so I haven't done anything to either side right now. But in order to make it continuous, let's divide by that delta t on both sides. So what I actually get is dA dt is equal to I over delta t plus d over delta t minus w over delta t. Okay, so like I said, this is a little bit of a leap in logic, but what I'm doing here is when we talked about that accounting method, it's heavily dependent, again, on what time step I choose. So if you were looking at 1 week, that would be very different than looking at 1 month. It would change the values of each of those interest rates, the deposit, the withdrawals. And so what I want to do is I want to remove my model's dependency on that. Okay, when it comes to accounting, again, we like to look at that in discrete levels, but for most of our models, we want to look at this in a continuous form. So what I'm going to do instead, I'm going to convert this to a rate. And so these will be continuous rates, and they will not actually reflect what I'm looking at in terms of accounting. But if I convert these to rates, we'll just use the lowercase of each of those letters. I plus d minus w. Okay? And so what these rates are saying is, okay, this model is now dA dt, so the change in my account over time, is equal to whatever the interest is, interest rate is, plus that deposit rate minus my withdrawal rate. And so this is the continuous form of that accounting equation. You can see how I could say anything I want in terms of establishing what time period I'm looking at. The way it's set up right now is continuous, and if you can convince your bank to give you continuous interest rates, then I need to switch to your bank. But what we'll see is this will actually give us the most money for our interest rates. Okay, next we need to determine how these variables are related. So our constitutive laws tell us, okay, how are these variables all related to each other? Do I just pick numbers? And the one that in our case matters, so deposits and withdrawals aren't dependent on what's there, but that interest rate. So again, we'll choose an interest rate, but interest is based on how much money is in our account, right? If you start off with $100 in the account at 4% interest, you'll earn 4% on that $100. If you start off with $10,000 in that account and you gain 4% interest, it'll be 4% on that 10,000. So we know that, so this is the interest rate only. And this we'll call, so I is going to be some constant k times a. So a being the current balance in there. Oops. And k being our interest rate. So for example, let's say 4%, I think is what we said, per annum. Okay, if we were to consider, and again, I'm going to have the continuous versus discrete discussion right now. In a typical account, we would see something like this. We flatline, and then this would be 1 year. We'd, oh, hey, I earned 4% interest, however much that is. And then we'd have to wait another year to gain that interest again, and then another year to gain that interest, right? This is how typically you're going to see these rates increase. Now, when we look at a continuous method, which is what we're talking about today, we're just going to get a straight line like this, right? It's not depending on that that rate in terms of the time dependency, because that was our step in step 3, is removing the time dependency from the equation. Okay. So the next one we need to worry about is, okay, so 5, what are our boundary or initial conditions? So this being kind of a growth problem, what we have is an initial value problem. And so the only thing we know is whatever our account balance will be at time equals 0. So what is the initial amount of money in there? And in this case, it's A naught. And we'll just say, because I know what it's like to be a student, it's $0. Okay, so we're starting with nothing. And so now that we've done, I know it kind of seems like we've talked about pretty obvious things in here. But what we can do is we'll show the final solution of what the problem that we formulated. So again, we'll go back to that continuous form of the equation we determined. So dA dt equals d minus w plus I. Not sure I did those in a different order. But dA over dt and equals, now let's replace, recall that I over here is equal to Ka. So we get d minus w plus Ka. So I know dA dt minus Ka equals d minus w. Okay, now this is starting to look like some of the problems that we've already looked at. This looks, it is a first order differential equation, and what we can look at is, okay, we'll say, again, this is what's changing, because this is our derivative, right? And all of this is why it is changing. And that's really key when we do these problems. And one of the things I really want you to pick up on when you're formulating them, what are each of the variables saying, right? If you are including terms, why are you including terms? If I were to say, so this becomes really important in something like simplification, right? If I said that you don't take any money out of this account, well, why do you have W in there then? Now we know we can assume that W is equal to 0. So understanding each of your variables is really, really critical. in this. Okay, so we've got our problem now. Now let's go and let's solve it. Okay, in this case, it's a first order linear differential equation. Linear ordinary differential equation. And we're actually going to use the integrating factor method. So no, I haven't gone through this method in class. It is in the math review. So integrating factor method says, okay, if I have something that looks like this, dy dt plus some function of t times y equals another function of t. If it looks like this form, then I know my solution takes the form of y equals the integral of v q of t dt over v plus some constant c over v, where v is equal to e to the power of p of t dt. Okay. In this case, when we look at our equation, I'll write it again here. So dA dt minus ka equals d minus w. Okay. This negative k is our p of t. This is our q of t. It's very important that you have the equation in the right form before you start. So pretty simply then, v is going to be equal to e to the negative kt. And I know that y will be the integral of e to the negative kt d minus w, minus w dt over e to the negative kt plus c e to the kt. And you know what? I'm going to correct myself here. This is not y anymore. This is just a in this case. Okay, and if I go through and do the integration on this one, what we'll find is that I actually just get, because the integral just comes out of these here, or so the negative k, again, if you take the integral, it's 1 over negative k, so I get a is equal to d minus w over negative k. Okay, so that's from integrating the top term, e to the negative kt over e to the negative kt plus ce to the kt. Okay, these two are going to cancel, and what I'm left with now is a is equal to negative. Actually, let's just change this order of those signs. W minus d over k plus c e to the kt. Okay, and this is our function now that we can work with. So this is a continuous function. In order to solve it, we need to put our initial conditions in. So we'll solve this in the general case in this case here. So we'll just call it a naught for now. And so I know a at 0 equals w minus d over k plus c. And that's going to be equal to a naught. So therefore c is going to be equal to a naught plus d minus w over k. Just switching those terms again so I don't have to have them all over the place. Okay. If we plug c back in, then I know my final equation is going to look like this. I get w minus d over k plus a naught plus d minus w over k e to the kt. And I'm going to write that in a much nicer form, and we're just going to say a t is equal to, we'll bring the d minus w outside, d minus w over k e to the kt minus 1 plus a naught e to the kt. Okay, so this is our formula here for continuous interest. Right? This doesn't take into account the fact that when we calculate interest, then your bank calculates interest. It doesn't calculate it based in a continuous form. It does it in a discrete method. And that's what we're going to look at next really quickly here. This one here is what we would consider to be our exact solution in this case, especially if we were dealing with a non-bank problem. But let's look at a numerical solution. And so a numerical solution is actually going to be a lot closer to what the bank will do because, again, we're moving back to that discrete form. Right? So in this case, we can look at our equation that we derived, dA dt equals Ka plus d minus w. And if we just look at this, we can say, well, I know my a at n plus 1 minus an, right? So this is all I've said on the left-hand side. I'm just writing this explicitly now. Equals Ka plus d minus w. And let's move that around again. So we have a at n plus 1 is equal to an plus delta t times Ka plus d minus w. I've used n's here. It's just a different index. In this case, now we have the choice. As we've done before, we can look at our different types of numerical methods. So we have the explicit Euler, the implicit Euler, or the RK4. Now, again, if you think about this this problem, it actually doesn't make sense to choose one of these because your bank doesn't say, hey, I wonder how much money you'll have in the future. They just look at what you have now. So for this example, doesn't really make sense for us to use anything but the explicit Euler. And so that's going to be based on what money you have here. Okay. So if we go through and we actually almost done here, just going to calculate the values determined by each of these, and I'll show you kind of what the difference is. Let's set up our problem, and we'll say, okay, once again, a naught is 0. We'll say our discretization is at 1 year. D, so our deposit rate is $1,200 per year. We're not taking any money out of this, so 0. And then our interest rate is going to be 0.04 per year as well. Okay, so if we look at this, again, using the numerical or just discrete, we would say, okay, well, let's set this up. A0 is just going to be 0. A1 will be equal to 0 plus, and then 1 year times my interest rate, 0.04 times I have nothing, plus my deposit rate, so 1200, plus my withdrawal rate, or minus my withdrawal rate, which is 0. And so at the end of the year, I'll have $1,200. This makes sense. You don't have anything and it's compounded annually, and you add $1,200. You'll have $1,200 at the end of the year. Year 2 is where we make a little more interest. So we have $1,200 at the end of year 1, beginning of year 2. And then plus 1 year, 0.04. Now we're actually gaining interest on this. We're still depositing the same amount, and we haven't taken anything out. And so with that interest, we've earned $2,448. So we've earned $48 in interest. And we're going to look, for the sake of comparison, at the 40th year. So start now, and you might have some money later on. 114,030.60. Okay, so $114,000 if you compound annually, and you're adding $1,200 per year. So now let's look at the continuous. And in our case, this is the analytical formulation. And let's see what kind of money you can make if you could convince your bank to compound continuously. So again, A of t is d minus w over k, e to the kt minus 1 plus a naught e to the kt. Okay, and $1,200 in deposits, no withdrawals, over 0.04 is our rate. Then we say e to the 0.04 times, and my t is 40 years, minus 1 plus, sorry, this is all in brackets, and then plus, again, my a naught is 0, so this is just plus 0, and 118,590.97. So it's approximately a $4,590 difference. So, I mean, over 40 years, it's not too bad to miss out on, but yeah, hopefully you guys were able to follow along. What's important about this one is not so much, again, the difference between an accounting problem and the engineering problems we're going to be doing is significant. What I want you to pick up from here is okay, what did we do for this integrating factor method? So that's right here. Integrating factor method, and that's in the math review. It's not something I'll be testing directly, but it's something that you should know about. And then as well, okay, how did we go about the setup and the formulation? So talking about things like the constitutive laws. So how are the different variables related to each other? Talking about continuous variable, making our variables continuous. What is the conservation law? So in our engineering problems, again, it's going to be things like mass and energy, not so much finance, but still the same idea applies. You have to have a law for how things come and go. Okay, so hopefully that was helpful and not too dry and boring. Yeah, thanks for listening along.